Hello, my name is Gabriel Miguel Gomes Guerreiro, and today I'll be presenting the work done in cross-country faults in resonant grounded networks with mathematical modeling, simulations, and field recordings. This work was done in a partnership between Hitachi ABB Power Grids and the Royal Institute of Technology KTH in Sweden. So first we will talk about resonant grounded networks and the origin of cross-country faults. After that, we will talk a bit about mathematical modeling of these faults. And finally, it will present some simulations on the system topology and define some different fault types and patterns. At the end, we'll draw some conclusions and future studies. So let's begin by defining what resonant grounded networks are and the origin of cross-country faults in such systems. Resonant ground networks were first invented by Valdemar Petersen in 1916, and they are also known as arc suppression coil, Peterson coil, compensated earthing, among other names. Nowadays, they are mainly used in Europe and Oceania, but they are starting also to be used in North and South Americas, and they are characterized by a variable adjustable inductance connected between the neutral point of the transformer and the ground point. They are used to compensate for the capacitive current during a single phase to ground fault, and what also brings increase of reliability and continuity of power as currents are very much reduced in the fault location. They can be either centralized or decentralized, and what that means is that you can either have one single coil in the system or you can have multiple coils in the systems. Usually, decentralized compensation is used in higher voltage levels and with higher capacitive current due to current limitations through the coils and long cables in the system. For such networks, the behavior during a single phase to ground fault is interesting to be studied and to be understood. If we consider a simple non-loaded radial three-phase system, where the terminals here, there are no loads connected to it, and the neutral point connected through a Peterson coil, therefore this is a resonant grounded system. We can consider a fault in phase A in front of the source with a fault resistance of RF, and we can instantly see that the healthy capacity, a phase shunt capacitances start to discharge, and at the same time a voltage builds up across the resonant coil, the Peterson coil, which makes this a current also flow through it, which is 180 degrees shifted from the capacitance, and in the fault location point, the summing of these two currents yield values very close to zero, 0 amperes, depending on the compensation of this coil. Another important factor is that when such faults occurs, the neutral point is displaced. In such cases, if you have a solid fault, which means that your fault resistance is zero or close to zero, your neutral point displaces almost to the nominal value of the pre-fault phase to ground voltage of the faulted phase, and the other healthy phase is the square root of 3 of the phase to ground nominal voltage. And on the other hand, if your fault has a higher resistance, your neutral point is displaced, but not entirely to the nominal value, as there is a voltage drop also across the fault resistance. Therefore, the healthy phases, they are between the nominal phase to ground voltage and the square root of 3 phase to ground voltage, which is the same as the phase to phase voltage. So this neutral point displacement is the very principal cause of these cross-country faults. They are defined as two simultaneous phase-to-ground faults, but different than classic high-voltage evolving faults, these cross-country faults are not in the same location. They are in different locations and they happen also in different phases. The probability of occurrence of these faults in resonant or isolated networks after their first fault and neutral displacement are during the overvoltage transient or when a certain point of insulation is already damaged. So if you have the two healthy phases, the two remaining healthy phases with their nominal value over a square root of 3, then this insulation is further stressed and is prone to be to open up arcs and discharges. The probability also increases if this first fault, this first phase to ground fault, is allowed to continue for longer periods, as it is the case in some other countries where these faults can be kept in the system running, with the system running for up to some hours even. So now we can go quickly through this mathematical modeling of cross-country faults. So in order to mathematically represent cross-country faults, in this paper we use two-port networks. They can be connected, the terminals of these two-port networks can be connected in different ways, where for phase-to-ground faults, we would connect in series connection for each symmetrical component two-port network. If the system is more complex than that, then the impedances, to find the impedances that would go in the two-port network, we would need to find the admittance matrix and then invert the admittance matrix to find the impedance one, then to build the two-port network. Furthermore, for if the system is balanced pre-fault, then only the two-port, the positive sequence two-port network has voltage sources. Finally, since the fault is not in the same, the two faults are not in the same phase, the fault which in phase B or phase C needs to use phase shifting transformers in the positive sequence and negative sequence to port network. In this case, the fault on the right side is in phase B, then we need to use the phase shifting transformers here. Analyzing some quick results, it's possible to see that between a comparison of calculated and simulated in our SCAD system with 5 ohm fault resistance in this case, it's possible to achieve quite accurate results for any fault resistance and measurements at any location, both in the bus and also in the currents and voltages in the fault location, as well as the currents and voltages in other places. It's always possible to retrieve the values and calculate them back to any place in the system with two-port networks. So the simulations. So the system topology for the simulations is presented here. It's based on a 47 kV network, based on a Norwegian network with real data obtained from the utility. And the intent here was to simulate faults across the system to validate patterns in different locations. There are here 5 fault positions from F1 to F5, and also we can observe that the compensation here is decentralized, meaning that we have 3 coils connected to the 3 main transformers of the system. The system was used to identify our 4 different types of faults with different patterns from type 1 to 4, and the full data information of the system is present in the paper. First, we analyze faults type 1 and 2, which are between faults F1 and F2 here. And basically, they are 2 radio and or ring feeders. And the switch 1 is used to connect them in radio or ring. Type 1 is a feeder with a single in-feed connected radially, and the type 2 is feeder with single in-feed connected in ring. So comparing types 1 and 2, first we see that the measurements are done here in breaker 2. So when the fault happens in a radio connection, we can only see one current flowing in the forward direction feeding the fault F2 here. And that also gives us a residual current in phase with this phase current, which is very similar to a single phase to ground fault in a solid grounded system. However, when we have ring connection, meaning switch 1 is closed, we start seeing a current flowing 180 degrees shifted from the current in the protected line, and with a lower magnitude, since this fault is a further distance from the measuring point. This causes a lower residual current that can be even further seen when the fault in the neighboring feeder is starting to get closer to the end of the line, meaning the ring connection. This current here, which is feeding the fault in the neighboring feeder, starts to increase, as we see here in this measuring point breaker 2, and the residual current starts to decrease. This here yields a negative result for protection functions such as impedance-based protection or residual overcurrent protection, since in some cases this residual current can be very low and very similar to a phase-to-phase fault, even though your protection needs to be for phase to ground fault. It's possible to observe here a comparison between the simulation and real recording for type 1 faults radio feeder. And in here we can see that the simulation and the real recording obtained from the Norwegian network, they are very similar, in meaning that when the feeder is connected radially, we can only see one current flowing in the forward direction feeding the fault, and the other faulted current it's not possible to observe in this feeder. But at the same time, if we analyze the voltage behavior, it's possible to see that the two faulted phases have the lowest two phase voltages. It means that this is one of the patterns that can be further analyzed when trying to identify cross-country faults. Now we should analyze cross-country faults type 3 and 4, which in this case are between faults locations F1 and F3. One fault is in the radio feeder, which was already explained, and the other focus here would be in this interconnecting line with double infeed, where breaker 3 measuring point and breaker 4 measuring point are located. As we can see here, breaker 3, also known as T cross-country fault type 3, is a measuring point where it's sitting between the faults. So one fault is in forward and the other fault is in reverse. On the other hand, breaker 4 here is a measuring point where both faults are forward direction, meaning that this fault is forward and this fault is also forward. Now, if we analyze the faults type 3 and 4, first we can analyze breaker 4, which is the one seeing both faults forward. As we can see, the fault in forward direction closest is the highest current, and followed by the fault in the other fault in the other feeder, the phase C here, and also an increase in phase B here, which is non-faulted. This is explained due to the lack of path for the residual current to come and return, and also because the two faults are not in the same location, so the currents are also therefore not the same magnitude. So there needs to be a compensation done by the system with an increase in the non-faulted phase B, which comes from one source and returns through the other. Here in this case, there's a very low residual current, which is only originated by the Peterson coil here, feeding the fault here. So this residual current is not in phase with any of the faulted phase currents, and therefore can cause problems with residual base protections. Furthermore, with breaker 3, which is sitting between the faults, since one phase current is flowing in the forward direction and the other is flowing in the reverse direction, and furthermore there is this compensation for the lack of residual current on the other side, we have the three-phase currents in phase. These in turn yields very high residual current and also can cause overreach of protections such as residual overcurrent or impedance-based protections. We can furthermore see this when comparing the residual currents. On one side, breaker 3, we have a high residual current, and on the other side, breaker 4, or type 4 in that case, we have a very low residual current, which is only referred to the Peterson coil sitting behind the measuring point. Finally, we can observe a comparison between a simulation and real recording for type 3 types of cross-country faults. And this is when the relay is sitting between the faults and the three-phase currents, they sum up. And we can observe here that the simulations could be validated and the pattern can be verified in real systems, as the simulation is very similar to a real recording. And this is a proof that these cross-country faults can be of great interest and at the same time great complexity to protect against. As conclusions and future studies from this paper, we can evaluate that cross-country faults can be calculated analytically and yield accurate results. And at the same time, we defined four different patterns of cross-country faults that can be identified in the power system. Type 1 and 2 is they are referred to single in-feed with radio or ring connection, and type 3 and 4 refer to line with double in-feed. Usually these types are present in the same line where the relay at each side sees one type. Cross-country faulting lines or cables with double in-feed can be extremely challenging to protect against. Voltage and current patterns can especially affect distance protection and direction calculation. Uh, as future studies, transient behaviors can be of great interest for analysis and effects, as well as phase shift and anomalies in the residual current magnitude need to be addressed in several systems. So thank you very much for everyone's attention. Have you got any questions?